Okay. So, thanks for having us. Our plan is to have me speak for about 15 minutes, leaving enough time for Flavio to talk about our latest paper. Even though Ethan asked us specifically to talk about our latest work, I'd like to stress that this is a long and productive collaborations with my math colleague Hong Chuan, who is in the audience. The motivation for our work is to understand the dynamical systems that governed late-time cosmology. Now, Flavio will draw upon results from some earlier papers. So my job is to warm you up for his talk by reviewing some of the key results. Um, as reflected by your votes in the first open mic, we are in an exciting time for cosmology. While this is too early to tell, Desi gave a tantalizing hint of a possible crack in the standard lambda CDM model. Now, if dark energy is not a cosmological constant, what is it? Is it quintessence or something even more exotic that violates the null energy condition? As you can see from the plot on the left, the data points that drive the equation of states to smaller than -1, known as the phantom regime, have very large error bars. But whether dark energy is phantom or not, it seems like the time is right to reinvestigate the possibility of a time-evolving dark energy. Now, phenomenologically, you can ask what model best fits the data. And how do we model phantom behavior? And is that even necessary? There's certainly no shortage of ideas. For example, axions which coupled derivatively do not lead to long-range force, which is one of the main hurdles to overcome for quintessence. Or it could possibly, or maybe it's an exponential potential, which is commonly found in string theory. Or maybe it's a negative curvature or a short-lived de Sitter maximum. All these possibilities are on the table. Now, the dark matter dark energy coupling that Flavio will talk about is versatile enough to realize not only acceleration, but an effective phantom behavior. Now, the fact that you are coming to a swampland seminar shows that you are not satisfied with just modeling dark energy. You would like to know what is it microscopically. A fully explicit de Sitter vacuum in string theory remains elusive, even though tremendous progress has been made in the past few years. As many of you have argued, swampland considerations suggest that de Sitter vacua, if they exist, are short-lived. Now, I think it's an exciting time to not only try to model dark energy, but to find a UV-complete model that describes the current acceleration. The challenge is real, whether the source of dark energy is dynamical or not. And in this talk, we will focus on time-evolving dark energy, mainly to highlight the new challenges and possible new opportunities. And investigating these questions, of course, would also help us sharpen some of our swampland criteria. Now, observations require only an equal or less of current acceleration. So you may ask, how limiting are the swampland constraints on short-lived acceleration? So this talk is divided into two parts. I would do part one. I will review some earlier results, which naturally led us to a less explored direction. Flavio will explain how a dark matter dark energy coupling can relax some of these constraints. So part one, bound on late time acceleration and attractor behavior. Now, for simple models, particularly single field models, perturbatively stable solutions and sometimes even global late time attractors are known exactly. For example, the attractor solution for a single exponential is known, whether the spatial curvature is flat or negatively, or spatial slice is negatively curved. Now, to see whether the universe is accelerating, we can look at the time variation of the Hubble parameter. This defines for us an epsilon parameter. We can equivalently state the criterion for acceleration in terms of the equation of states. They are related by a very simple linear relations. This is to be contrasted with the slow roll parameters defined in terms of gradient of the potential commonly find in swampland criteria. If the kinetic energy is negligible, then the two notions of epsilons are the same, but if the kinetic energy is not negligible, they are generally different. Now, transient solutions is easy to arrange. You can imagine that the scalar field would climb up momentarily, but this only gives you a few EFOs. For single field exponential potentials with flat spatial slices, these are the attractive solutions. If the exponent that appears in the potential is below a critical value, gamma d, we have scaling solutions where the potential and the kinetic energies are equally important. They scale with time in the same manner. Above this critical value, we have kination, which basically means that the potential is effectively zero. Now, this results by itself does not rule out cosmic acceleration, but the asymptotic Transplancking censorship conjecture and the strong de Sitter conjecture put a bound on this exponent, which translates to a bound on the epsilon parameters to be bigger than or equals to 1. Now, technically, acceleration is not forbidden because you could imagine that the epsilon parameter approaches 1 from below. The universe accelerates indefinitely, even though there's no cosmic horizon. However, there's no known example in full-fledged string compactifications that give you this behavior, this late-time behavior. There's always something else that makes the epsilon parameter slightly bigger than 1. And you will see shortly why this is the case. And an independent argument was also given by Arlick and collaborators. Now, in the interior of the field space, Transplancking censorship conjecture is weaker, and cosmic acceleration is still possible. So if the spatial slice has negative curvature, the attractive solutions are also known. Below a different critical value, this time is 2 over root d minus 2, we have scaling solutions. And above, epsilon is equal to 1. And this is the borderline case where acceleration is possible, yet there's no cosmic horizon. This is in line with a conjecture made by Arthur and collaborators. So how do we understand this late-time behavior physically? So imagine if you have a cosmic fluid with a constant equation of states, the energy density evolves with time as follows. And it's easy to see then that whichever component of the universe that has the smallest equation of state would dominate eventually at late time. Now, the evolution of energy density for the scalars is more involved because the equation of state depends on the field, which in turn depends on time. So we cannot make such a simple argument. However, when the attractive behavior is reached, the equation of state reaches a constant value. Now, what makes spatial curvature special is that it acts like a fluid that saturates precisely the strong energy condition. So if you look at the plot on the right, this is the component of the universe that has the smallest equation of state, comparing the kination phase and the scaling solution phase. So this would give you the dominant contributions to the energy density, and translating that to the epsilon parameter, that's precisely 1. And this explains the late-time attractive behavior found earlier. Now, the dynamical system is still tractable even with an additional kinetically coupled axions. So the field space is negatively curved, as commonly found in string compactifications. In fact, if you look at any supergravity Lagrangian, you will find these structures for the kinetic energy for the scalars, for the non-compact scalars, and for the axions. Now, perturbatively stable attractors are known. And in fact, there was a very nice paper by Thomas, Damien, and Filippo last week studying this dynamical system with a UV-motivated potential. So there are three phases for these dynamical systems, depending on the potential and kinetic couplings. So gamma is the potential coupling, lambda is the kinetic coupling. As you can see, in one of these phases, epsilon is effectively reduced due to the kinetic couplings. We have generalized these results to high dimensional field spaces as well, but accelerated solutions in a full-fledged string compactifications remains elusive. So one may ask whether multiple field interactions could provide us a way out. And naively, it seems so. So up to this point, I was describing to you only one field, or perhaps with an axion. But what about multiple fields? Asymptotically, as the field rose to large values, there always exists a basis where all except one fields are stabilized. So let's call this unstabilized field phi 1. And you can see that the effective coupling for this unstabilized field is smaller than what appears in the individual potentials. So this seems to offer a loophole to the constraints that were found earlier for the dynamical system study. But not so fast, because there seems to be a universal obstructions in string compactifications. In string perturbation theory, different order terms are weighed by the 10-dimensional dilaton that I call big phi. When you reduce the theory to lower dimensions, there are two universal moduli. One is this 10-dimensional dilaton phi, and the other is the Einstein frame volume. Or by a change of basis, you can go to a frame where the two universal moduli are the d-dimensional dilaton and the string frame volume. What's interesting about this d-dimensional dilaton is that the exponential coupling is positive definite. This is not the case for the 10D dilaton. And furthermore, it is bounded from below by precisely 2 over square root of d minus 2, corresponding to potential generated at tree level in string perturbation theory. So any higher order term would just make this exponent bigger. And this translates to a bound on epsilon to be bigger than 1. And this is consistent with TCC and the strong de Sitter conjecture. So in our paper, we suggest several ways out of this universal bounds. Besides field space curvature and spatial curvature, if the theory is not at weak coupling, or if the d-dimensional dilaton is stabilized, or there exists potential terms that are negative, even though the overall potential must be positive for acceleration to occur, there could be a combinations of terms, some of them takes negative values. In such cases, the universal bounds may be relaxed. And now Flavio would explain how this bound may be relaxed with a dark matter, dark energy coupling. And I could.
Okay, I'll share my
Yes,
slides
please.
now.
Yes.
Okay. Thanks everyone for being here, and thanks to the organizers for giving me the opportunity to speak. I will resume from the point where Gary ended, and I'll discuss dark matter, dark energy couplings, and suggest a few possibilities to overcome some of the limitations that Gary illustrated in order to get a long-lived phase of expansion with epsilon less than 1. So to start, I will review an old idea which concerns dark matter, dark energy couplings and violations of the null energy condition, because this will be instrumental to understand the later results. So as we all know, violating the null energy condition leads to energy density, to an energy density that grows over time. This is obvious from the point of view of cosmology, because as Gary mentioned, for a fluid with constant W parameter, the energy density scales like 1 over A to the d minus 1 times 1 plus W. And with the neg violation, so W less than minus 1, rho grows as the universe expands. Of course, this is somewhat puzzling, and there are a few possible explanations. An obvious one is a scalar field with a negative kinetic energy, which induces a phantom behavior. However, this is quite tricky to deal with. There are instabilities, and therefore there are possibly alternative explanations that might be more desirable. And an obvious one is a situation where there is a second fluid that decays into this original fluid X. And if the transfer of energy is sufficiently fast, effectively rho grows over time. Now the question then is how to model a suitable coupling between these fluids. And an obvious answer is to just look at an example where we have a first fluid, non-relativistic dark matter, whose energy density scales proportionally to the number density and to the mass of the dark matter constituents. And then a second fluid is represented by a scalar, which will be our dark energy. Now, if the mass is field dependent, the energy density evolves as illustrated here. So it doesn't just redshift with the inverse volume with 1 over a to the d minus 1, but it also evolves with time because m evolves with time. Now, this coupling between dark matter and dark energy makes the definition of the energy densities ambiguous in the sense that it's somewhat arbitrary what we define as energy of the fluid and energy of energy of the scalar and energy of dark matter. For instance, you can add and subtract a term that takes a reference mass at a time t0. This term redshifts just with 1 over a to the d minus 1, like a dark matter with constant mass. And then all the phi dependence is packaged into something else, which reads like rho phi plus rho dm times 1 minus m dark matter at time t0 divided by m dark matter. If we consider this as an effective energy density for the scalar phi, then by writing a continuity equation for this effective energy density, we find a different W parameter for phi. It's not just W phi, it's W phi divided by 1 plus rho dark matter over rho phi times 1 minus m dark matter at time t0 divided by m dark matter. And it's apparent that if this bracket is negative, so if the mass at the reference time t0 is larger than the mass at another time, then the denominator is less than 1. So in absolute value, it's easier for rho effective to be larger than 1, or if you put the sign, it's somewhat easier to get effective parameter which is less than minus 1. This is an old result, but in fact, recently, in light of the DAISY evidence for a phantom regime, this has also been suggested as indirect evidence for dark matter dark energy coupling. It's just about how one packages the field dependencies in the contributions to the energy density.
One comment I have, Flavio, here, just for people who are not familiar. So in the original work of Huri et al., they had assumed that the reference time is now. And for them, they were assuming that the dark matter now should be higher for this to work. Yeah. Whereas they wanted the dark matter increasing with time for this to explain the phantom behavior. Whereas actually we point out in our paper that actually that's not necessary. And indeed in our model, the net dark matter mass is going down. So therefore, the initial what you take not is not now, but actually the time that you're setting your parameter to be set to that value, to a fixed value. Just a comment for people who are not familiar.
Yeah, thank you. Yeah, exactly. So now this is not the end, and actually this slide is very important for what we're going to talk about next. So if raw dark matter scales not just with the redshift of the volume, but also with the dark matter mass, the continuity equation is modified. So here usually you have 0 if you want things to redshift with 1 over the volume. Instead here we need to add this phi dependent part. And in turn, in order to have a total energy density, which is still rho phi plus rho dark matter, you also need to modify the cosmological time-Gordon equation. So the second derivative of the field as the Hubble friction term, the gradient of the potential, and then it also has an extra contribution. And practically, this means that there is an effective potential, U, which is the original potential, V, plus this scale factor dependent term. And so far, we have not specified the properties of V and M, but intuitively, it's obvious that if the derivatives have opposite slopes, if the profiles have opposite slopes, if the derivatives have opposite signs, effectively we generate a time-dependent minimum. Eventually, this potential U, as the scale factor goes to infinity, will approach the original potential V. But for a long time, you have a time-dependent minimum. So this is not it cannot give a de Sitter solution, of course, because this minimum shifts towards the right as it evolves. But it seems to suggest that it's somewhat easier to get a smaller kinetic energy, which favors a lower epsilon value. Both with this choice of signs and other choices of signs, this scenario has a long history. So
Flavio, can I ask a question about?
Yeah, sure.
Sorry. So in the fact that this has a local minimum, is that relevant for the dark energy dominated era or dark matter dominated era? Because taking phi to have a value that is right at that minimum, especially in the dark matter dominated era, would be a lot of fine tuning because you're asking via phi and dark matter to compete with each other, right?
Well, there's always going to be a minimum. Maybe one contribution will dominate, like whether it's V or the dark matter term, but especially at equality, they will be comparable. But even before dark matter dark energy equality, the shape will be qualitatively this one.
Oh, I understand that the shape is like that, but sorry, maybe I misunderstood. Were you claiming that the scalar field will be in the minimum as it drives away?
Well, okay. No,
Are you taking that solution?
Okay, that's not necessarily. Of course, it depends on the initial. It might be, yeah, generally it will not be. What I will discuss is a asymptotically stable solution. So the field will be evolving slowly towards the right, but it doesn't have. Yeah, it's not necessarily the minimum.
Yeah, so this is actually an important point that Alec is raising. So original motivation by papers like Hori is, as you say, to find the minimum and be near it somehow. And that is actually not very natural. And in our model that we studied, we are nowhere near the minimum. And in fact, it is very artificial because dark matter or dark energy, one of them dominates at one time or the other. And so to be near the minimum where you're both are equal value or relevant values, sharp fine tuning in field values, you're far away from where you would want to be anyhow. So it's not very natural actually to have a minimum, even though there would be a minimum in the case that you're saying, but that was their motivation, but actually that's not the natural thing, and that's not what we found fitting the DESI data. But then, yeah, please continue.
Yeah. So I agree. So what I'm going to describe is a linearly stable solution. So it doesn't really depend on the initial conditions. There is a sort of memory loss of the initial conditions, and it's valid at late times. So you don't need. I don't know exactly where the field is initially. We don't need to know. What I'm going to describe is just what will happen if you wait long enough. Okay, so the dark matter dark energy couplings. So just a recap. Observations trigger interest in dark matter dark energy couplings, and they can have the practical effect of lowering a neck fulfilling state parameter with an effective neck violation, as I showed. Now, a natural question that we can ask is, can we exploit the same principle to lower a sec fulfilling state parameter down to one that violates sec, the strong energy condition? The answer supposedly is yes, based on that plot, even though there are some objections on the initial conditions. But what I will argue is that if you wait long enough, there's going to be an effect of lowering the state parameter that you would get without the coupling. And then the second question is, if we can violate sec, can this last for a long enough time, where long enough will be defined in a moment? And we will see that the answer to this is a bit trickier. So for definiteness, we will explore solutions with exponential couplings. So both the mass and the potential go exponentially with one field direction phi. Before I go into the details, let me also remark that there is a long history. So the study of interacting dark matter dark energy models has been performed for a variety of couplings and for short-lived transient solutions in particular. So in the chameleon literature, they studied both short and long-lived solutions with exponential masses, but typically they didn't take exponentials in V, which is instead is more natural for from a swampland perspective. Then in these recent papers that were mentioned, exponential couplings have been studied, or things that have maybe a floater region closer to the bulk, but with a focus on short-lived solutions. And dark matter has also been modeled with additional scalar fields that, for instance, oscillating near a minimum can serve as dark matter. So here you see beyond phi, you also have a field chi with some quadratic coupling to phi, or in an even more recent paper, the focus was on exponential couplings, like we did. But what we will do is focus on linearly stable solutions, so solutions that, at least mathematically speaking, last arbitrarily long. So as I said, we will consider exponential couplings. So dark matter mass is exponential of beta phi, and the potential energy is e to the minus gamma phi. The parameter space is two-dimensional. We have gamma and beta. Without also generality, of course, we can take a definite sign. We chose to take gamma as positive definite, but beta can be positive or negative. And it turns out that the linearly stable solutions are completely classified. There is a scaling-like solution, which is the same that appeared in Gary's slides, where the energy density of dark matter goes to zero more quickly than the energy density of the scalar. Then there is a kination region where formally the potential also goes to zero. So you only have kinetic energy. Then here in yellow, you see a kination tracker region where formally the potential for the scalar is zero, and the kinetic energy and the density of the fluid are not zero. And then there is the one that I will argue is the most interesting solution, which is for our purposes, which is the one that we call the dark matter dark energy coupled solution, where the kinetic energy, the potential, and the energy density of dark matter are all non-zero. The reason why we will focus on this is because we are interested in linearly stable solution that allow for an epsilon value below 1. So all this area that I grayed out has a corresponding epsilon larger than 1. So we are left with these two possible kinds of solutions. There's the scaling solution, which is interesting in its own way. Gary talked about it. But in order to get acceleration, it always requires gamma parameter that violates the strong energy, strong de Sitter conjecture, and also the value singled out by the TCC in the asymptotics. There is, however, another region for this solution in green, which allows for epsilon less than 1, even when gamma is large, if you have a large enough beta. And so let's explore this a bit further. Epsilon is d minus 1 over 2 times 1 over 1 plus beta over gamma. It has a h parameter that goes like 1 over t, phi going like 2 log of t, and the energy density of dark matter goes like 1 over t squared, like in all these kind of solutions. course, we're interested in a UV embedding with epsilon less than 1, which in D larger than 3, of course, requires beta positive. So this of course raises the question concerning the cutoff, because the dark matter mass grows polynomial in time. It goes like e to the beta 5, it goes logarithmically, so the mass grows like t to the 2 beta over gamma. Of course, this will reach any cutoff eventually, but even more dramatically, if the EFT cutoff is below the species scale, and you take the species scale, you assume the species scale to fall off exponentially in this scalar phi, then this will go like an inverse power law of t, and there's going to be at most a few Hubble times before the mass of dark matter will cross the species scale. So the question is there a way to make physical sense of something that lasts for a long enough time? Well, what we argue in the paper with Gary and Hung is that because we are treating dark matter as a cosmological fluid made out of non-relativistic constituents, it is not necessary for this thing that we call M dark matter to be below the cutoff. The fluid is just a classical source of energy density, and in principle, it doesn't need a microscopic field to describe it.
Sorry, Flavio, can I ask a question?
Sure.
So for that solution to exist, you need beta to be sufficiently large, right? So for
Yes.
example, for gamma equals 1, what would your beta be? Would it be beta equals 1 almost?
I'm not sure. So if beta, so it depends on the
beta,
dimension.
I think to be 1.
You need to look at this plot. So if gamma is 1, it's presumably somewhere here. So you need.
So
I mean,
you
it can be
want 1 plus
computed.
beta
I
over-
don't.
Yeah, you want 1 plus beta over gamma to be the same as that 4 over 2 over gamma squared. So it would be beta
Yes.
of 1. So my question is do you do you think this would be relevant for the late time cosmology? Because so my worry is that, I mean, for example, the best fit numbers that we see, the beta is really small, it's 0.05. And
Yeah.
I mean, so I understand the intuition that you want the beta to be large enough so that it will drive you quickly to that local minimum of the effective potential, but that will make the dark matter mass too strongly coupled with the scalar field. It will not typically give you a good fit.
Okay, we didn't. Okay, so the couplings that are in your paper, yeah, they're somewhere like in this region, like they're in the scaling solution region. So if you want, okay, this if you take the couplings that you found with the fits with DAISY data, this solution is not relevant. You find the scaling solution, you find that dark matter eventually redshifts to 0 more quickly than dark energy. We are aware of that. But we are also exploring a different regime, which maybe doesn't fit data. The paper came out before we knew that your analysis would give small beta. So if you want, you can just take it as a thought experiment, like what happened with star beta.
But I see. But the point is that there is these attractor solutions. If you take beta to be sufficiently large enough, then there's an attractor solution.
Yes. Reiterating actually what Alec is saying, quite independently of our model, there's another issue that the fifth force in the dark sector would prevent beta to be less than 0.2, bigger than 0.2, sorry. Beta is bounded by 0.2 regardless of our data, regardless of our model. If beta is bigger than 0.2, you violate the fifth force conditions in our universe, which is already bounded. So this already will exclude the region you're describing, regardless of our model.
Okay. Yeah. Okay. Nonetheless, I mean, we can describe the solution, and we can also generalize it, as I will show in a moment, to multi-fields. And I'm not sure if in that case the bounds are so stringent. Like if you have 2 fields evolving.
Can I ask related to that,
Yeah.
Flavio? So you were saying that you wanted to have the field phi as an effective description for some microscopic object, so sort of like a proxy of just measuring like a force or whatever. Would the fifth force constraints apply also in that case?
I don't know in detail, to be honest. So you're saying, are you asking how to measure this dark matter mass as it evolves with time?
I guess they would. I guess they would. Yeah. Just like any other object, I guess. No, it's just like a mass depends on phi, so automatically that gives a force.
Okay, but I don't think that okay, maybe for this specific coupling, there are constraints that I'm not aware of, but in general, the mass of dark matter can be very large. Like if in models where it's like primordial black holes, I think it might correspond if you plug in some numbers to a large beta. Of course, it depends on the value of phi, but
There may be some bound on equivalence principle. I mean, otherwise, if they don't give additional forces, then there's a violation of the equivalence principle.
okay, maybe let's discuss this later. I'll go on for now.
Yep, please.
Okay. So as we mentioned, for instance, if there are dark microscopic objects which serve as dark matter made out of some dark particles, then they can have a field-dependent mass, and so we expect these dark macroscopic objects to also have a field-dependent mass. And even though we don't know details on, say, the binding energy or what keeps these objects compact, we can still parameterize the dark matter mass as a function of phi, and we took an exponential to have a computable result, but the phenomenon is probably more general. And there are also two further considerations. The dark matter Compton wavelength falls down with respect to the Hubble radius. You see lambda dark matter goes like 1 over m, 1 over lambda goes like h. So this ratio falls like t to the 2 beta over gamma plus 1. So the classical approximation in this sense becomes better and better over time. And also, another important observation is that even though the dark matter is growing, the redshifting due to the universe expansion is still sufficient to dilute the dark matter energy density away over time. Rho always goes like 1 over t squared.
Sorry, can I wanted to ask, this is something that we discussed, I think, this summer in Durham. So in a model like this where the mass grows, you also need to have like a proxy for what's the size of the objects that are giving you the fundamental constituents of dark matter, because if the mass grows beyond the Schwarzschild radius corresponding to the size of the objects, then they'll become Schwarzschild black holes and there will be no phi dependence.
Yeah, I will actually comment on that
Okay,
in a couple of slides. Yeah, thank you. So, okay, we can also generalize these results to multi-fields, to multi-field models. So we can take arbitrary models like the ones that Gary described with the potential, which is a linear combination, a sum of exponentials of linear combinations of the field of a bunch of fields phi, and dark matter mass is the exponential of always a linear combination of fields, and it's possible to see that there is a solution that is equivalent to projecting the multi-field problem onto gamma infinity. Gamma infinity is the vector, is the shortest distance vector joining the origin of coupling space with the convex hull of the exponential couplings that appear in the potential. Beta will point in some arbitrary direction. We can project it on gamma infinity. And the epsilon parameter is given by the direct generalization of the formula that holds for a single field problem, where you project everything onto the field direction singled out by gamma infinity. And as Gary mentioned, in general, we always expect the linearly stable solution to be the critical point solution with the smallest epsilon. So if you find a model with beta times gamma infinity positive, and with a long enough beta infinity vector, then we know that this dark matter energy coupled solution is going to be linearly stable, even with multiple fields.
Just a quick comment on comments from Kunrun and Alec. So gamma infinity is smaller. So effectively, that could make beta smaller and still have a sizable effect. But we don't have a model. So
yeah. Okay. Yeah, thank you. We can also make a few further comments, including I will get to Michael's question in a moment. In a swamp perspective, we expect the potential slope to be bounded from below by 2 over square root of d minus 2 when the field is near the boundary. By the distance conjecture, we also expect towers of light states becoming light with a mass gap that falls exponentially with phi. And for this parameter alpha, there's been a lot of work in recent years pointing towards a universal value that bounds alpha from below, 1 over square root of d minus 2. Now, in the case that we are considering, we want growing mass. So just to see what the numbers give, we can consider the dual towers in the opposite field direction. So formally, we replace alpha with minus beta. And we see that if we saturate the values, gamma and beta, with the smallest with the lowest bounds, we get epsilon, which is d minus 1 over 3, which again, when d is larger than 3, is at least 1, evidencing once again that this value is very special. We can still play, like we don't need to saturate these values. So even though we don't have a fully fledged top-down model, we can consider, say, a very simple example, curvature potential and a KK monopoly in 4D. In this case, epsilon is 6 over 7. So at least at this superficial level, it seems like the numbers that you find in compactification are a bit less restrictive than just with a scaling solution. Then there is a comment, however, that Miguel mentioned, which is a very natural requirement. If you want the dark matter Schwarzschild radius to always fit inside the double radius, you can impose a very simple condition. And somewhat surprisingly, this is fulfilled when 2 beta over gamma is less than d minus 3, which implies epsilon larger or equal to 1. So again, the take-home message is that when there is a arbitrarily long acceleration, the mass will grow so much that eventually it will outgrow the Schwarzschild radius will outgrow the horizon, which seems to be a limitation to the attainability of this model at arbitrarily long time. Then, as was mentioned, there's been analysis that was carried out for this model called the fading dark sector model, with stemming from arguments related to the dark dimension scenario. This model has been studied as a fit to DC data. So both the mass and the potential depend exponentially on a small field displacement with the 2 parameters C prime and C. And the analysis of this model with the DC data and supernovae dataset and CMB shows evidence for C prime, which if you compare at least in absolute value correspond to a very small number, as Alec mentioned. So beta is 0.05, and the absolute value of C corresponds to the absolute value of gamma, comes out to be also small, even actually smaller than the bound that one would expect near the asymptotics of boundary near the asymptotic of field space. And there is one preference for C less than 0. So in our notation, this would correspond to gamma and beta positive. Okay, then before concluding, there's also a kind of a bonus observation with this dark matter energy coupling. So in general, because of the string coupling and volume expansions, negative potentials tend to push the EFT away from perturbative control. For instance, if you have a volume expansion, typically with a negative potential, you have something like -1 over V to some power, which pushes V to 0. However, a coupling to a light hour of states can can allow for a dynamical evolution towards control regions. So we have this effective potential U minus, which is the negative exponential potential, and then the dark energy term, even with a decaying dark matter mass. It gives you this orange curve, which if you have initial conditions pushing the field in the right direction, doesn't go to towards the bulk. It goes towards asymptotics. Of course, the scale factor is not fixed, and this term goes down very quickly. So this potential is actually very steep. And we can show that even transient epochs can never have epsilon less than 1. To have epsilon less than 1, one may include a positive potential, e to the minus gamma plus phi, with gamma plus larger than gamma minus, and get this this magenta curve, which is quite different from the curve that one will get with just a positive and a negative term. So this is giving us more. With just a positive and negative potential, one would get ADS minimum, and instead, for at least a transient amount of time, with the additional positive term from the dark energy coupling, one can also have a shape which pushes the fields away from the would-be ADS minimum. Okay, so to conclude, we've seen that the dark energy coupling can induce a long-lived cycle violation, at least mathematically speaking. And we explored this as a new possibility to overcome the apparent limitations to long-lived violations of the strong energy condition near the field space asymptotics that Gary talked about. We highlighted two fundamental things. The first one is that the fundamental requirement is that the dark matter mass and the dark energy potential have opposite slopes, but there is no real other requirements, especially in initial conditions. And also the other observation is that dark matter may be simply treated as a classical source. Mathematically speaking, the dark energy coupled solution is linearly stable, and as I said, it is attainable without initial conditions that are fine-tuned, and at least in a mathematical sense, this solution is arbitrarily long-lived. However, as Miguel mentioned, very long-lived epochs of cosmic acceleration, so the solutions with epsilon less than 1, face obstructions due to black hole arguments. And finally, even though we didn't spend much time on that, multi-field extensions are also completely understood. Thank you.